Hello, good morning. My name is Angelis Urbano, and I am going to present a work titled Synthesis and Characterization of Strontium hexaferrite with cobalt ferrite for the adsorption of lead, cadmium, and chromium in contaminated water. Abstract. In this work, strontium hexaferrite, SfO, and a strontium hexaferrite with cobalt ferrite, SfO, CfO, composite were synthesized by the polymer complex method. The samples were calcined at 1000 degrees Celsius for 1 hour. The adsorption efficiency of the materials was evaluated using aqueous solutions containing lead, cadmium, and chromium ions at concentrations of 12, 20, and 60 mg per liter, adjusted to pH 5.0 for lead, cadmium, and pH 3 for chromium. The results show that the sample strontium hexaferrite exhibits the highest removal of lead with a maximum adsorption capacity of 17.16 mg per gram, whereas strontium hexaferrite with cobalt ferrite demonstrated superior efficiency for cadmium and chromium, with capacities of 8.15 mg per gram G per gram and 9.36 mg per gram, respectively. Introduction. Water contamination by heavy metals is a grave problem for human health. Among the most dangerous and polluting metals are lead, mercury, cadmium, arsenic, and chromium. Adsorption stands out as an economical and effective method. However, traditional adsorbent materials are difficult to recover. Consequently, to reduce this disadvantage, magnetic materials based on iron oxides were developed. Nevertheless, these have some disadvantages due to corrosion and low chemical stability. On the other hand, M-type hexaferrites are the most used materials as permanent magnets due to their low manufacturing costs, high magnetic anisotropy, high Curie temperature, and excellent chemical properties, high corrosion resistance, low electrical conductivity, and chemical stability. Recently, strontium hexaferrite has been used as well as in environment remediation, which would make it an ideal material for these applications. Methodology. Powders of strontium hexaferrite, SfO, were synthesized using the Pacini method. Samples were prepared using strontium nitrate, iron nitrate, citric acid, and ethylene glycol as precursor materials. The sample was prepared by dissolving stoichiometric amounts of metal nitrates and citric acid in deionized water, with a molar ratio of citric acid to metal nitrates of 4:1. After complete dissolution, ethylene glycol and citric acid were added. The solution was heated to 90 degrees Celsius while stirring to promote the formation of the polymer resin, which was pre-calcinated at 380 degrees Celsius for 30 minutes. The final product was sintered at 1000 degrees Celsius for 1 hour. For the synthesis of the composite strontium hexaferrite with cobalt ferrite, the sample was prepared by dissolving cobalt nitrate, iron nitrate, citric acid, and ethylene glycol. After complete dissolution, 1 gram of strontium hexaferrite powder was added, and the methodology mentioned above was followed. The structural characterization was performed by X-ray diffraction and scanning electron microscopy, while physiochemical characterization by determining active sites and isoelectric point. In Figure 2, we can see the methodology for determining active sites, which were determined by the acid-base titration method proposed by Boehm. The samples were prepared by adding 0.1 gram of material to a conical tube containing 50 milliliters of a neutralizer solution of hydrochloric acid and sodium hydroxide at a concentration of 0.01 normal. The samples were immersed in a water bath at 25 degrees Celsius for 5 days. The material was extracted, and a 20 milliliter aliquot was taken and titrated. Figure 3 shows the methodology for determining the isoelectric point. In this case, the samples were prepared by adding 0.01 grams of magnetic material, adsorbent, into a conical tube containing 25 milliliters of sodium chloride solution. The pH of the samples was adjusted to a range between 1.5 and 10 by adding hydrochloric acid or sodium hydroxide. Finally, the zeta potential of each sample was measured. The values obtained for each sample are plotted, and the point where the zeta potential is 0 is called the isoelectric point. The adsorption experiment was carried out using solutions of lead nitrate, cadmium, and potassium dichromate with concentrations of 12, 20, and 60 mg per liter. The chromium solution was adjusted to a pH of 3 while the cadmium and lead solutions were adjusted to a pH of 5. The experiment was performed by placing 50 milliliters of the standard solution in conical tubes and adding 0.1 gram of the magnetic material. Subsequently, the samples were immersed in a water bath at 25 degrees Celsius for 7 days, until equilibrium was reached. The pH of the samples was regulated and kept constant by adding HCl or NaOH solutions. The adsorbent was extracted from the solution using a permanent magnet. Finally, a 10 ml aliquot was taken, and the heavy metal concentration was estimated by inductively coupled plasma optical emission spectroscopy. Results and discussion: structural characterization and morphology. Figure 5 shows the XRD patterns of strontium hexaferrite, SFO, and the composite strontium hexaferrite, cobalt ferrite. In the diffractogram of the SFO sample, the hexaferrite peaks are still present. In the composite sample, the characteristic peaks of the cobalt ferrite are observed, while the peaks of the hexaferrite phase are present but are diminished. This is probably because the cobalt ferrite is in a higher proportion. Also, some of the peaks of the hexaferrite and cobalt ferrite coincide. The information obtained through the Rietveld refinement method for the crystal size, lattice parameters, density, and weight percentage of the phases in the samples is presented in Table 1. The results indicate that the average crystallite size of the SFO sample was 297 nanometers. While for the composite sample, the size of the cobalt ferrite phase crystallite is estimated to be 251 nanometers, and the percentage of cobalt ferrite is 53.15%. In Figure 6 shows the SEM images of the strontium hexaferrite and composite of hexaferrite CoFe₂O samples. The image shows the grains with a wide distribution of particle sizes for samples. Figures 6a and 6b for the SFO sample show two morphological forms. The first one is small cylindrical agglomerated forms that look like sponges. In the second one there are hexagonal pellets that are also more compactly agglomerated. These forms are characteristic of hexaferrites. Meanwhile, the SFO-CoFe₂O sample, as shown in figures 6c and 6d, is shaped like a compactly agglomerated sponge. In Figure 7 shows the magnetization curve MH obtained at room temperature for the strontium hexaferrite sample. As can be seen, the sample obtained the highest values of saturation magnetization and coercivity of 53 EMU per gram, and Hc equals 4.6 CoA, respectively. For physiochemical characterization, active sites were determined using the Boehm method and isoelectric point using zeta potential. The data are presented in Table 1. For the pure strontium hexaferrite sample, the following data were obtained. Total acid sites 0.4690 milliequivalents per gram, while total basic sites were 0.425 milliequivalents per gram, and the isoelectric point was found at a pH of 2.2. For the hexaferrite sample with cobalt ferrite, the total acidic sites were 1.025 milliequivalents per gram, while the total basic sites were 0.412 milliequivalents per gram. The isoelectric point was found at a pH of 2.8. In Figure 8, the zeta potential data for both samples can be seen. For both samples with a pH above 3, the surface charge of the material is negative. Finally, in Figure 9, we observe the adsorption capacity of both samples for chromium, cadmium, and chromium. In Figure 9a, we observe that the adsorption capacity for chromium increases, reaching its maximum value of 8.15 mg per gram with the cobalt ferrite composite sample, whereas for the strontium hexaferrite sample, the value is 7.43 mg per gram. In the case of cadmium, as shown in Figure 9b, we observe that the cobalt ferrite sample adsorbs more cadmium, reaching a maximum value of 9.36 mg per gram, whereas the strontium hexaferrite sample achieves a maximum value of 2.39 mg per gram. For the lead in Figure 9b, we observe that the strontium hexaferrite sample adsorbs more lead, reaching a maximum value of 17.16 mg per gram, whereas the cobalt ferrite sample achieves a maximum value of 12.51 mg per gram. Conclusions. In this work, magnetic strontium hexaferrite compounds were synthesized by the Pacini method to remove heavy metals from contaminated water. Results show that synthesized materials are capable of adsorbing lead, cadmium, and chromium. However, the SFO-CoFe₂O composite showed a higher efficiency for cadmium and chromium. Additionally, further tests are necessary to determine the mechanisms by which the contaminant is adsorbed and to enhance its efficiency. Finally, we can emphasize the high potential of these materials for industrial applications, owing to their low production costs and magnetic properties, which facilitate easy recovery and reuse.